Awesome, we're live. Okay, hello. My name is Kevin Wade. I am Mr. Wade on Twitter. This is live with Elixir and Phoenix. So this is a part of the OrgSync Lunch and Learn series, where us here at the OrgSync on the OrgSync development team will present every couple weeks about what we're learning and what's going on. So if you'd like to attend more of these live or watch them later on YouTube, then you can do that, and I'll show you how at the end. So today I'll be talking about Elixir and Phoenix. I have been playing around with Elixir for the last couple months and have really been enjoying it. I've really kind of fallen in love with the language and its power and its scalability, as well as the Phoenix framework on top of it. The Phoenix framework is a web framework. And also really its ability for you to create a full stack web application. So today's talk really is actually live with Elixir Phoenix and React. So this is not an intro to Elixir, it's not an intro to Phoenix. There are other talks that you can watch to do that. We're going to dive just like straight into the deep end, or at least into the middle part of the pool, and actually look at an example of how you might structure an Elixir and Phoenix application, and how you might use multiple processes within Elixir to all work together to create something cool. But we will do a crash course to get you up and going in order to make sure that we can talk through the demo and the code throughout the talk. So the Elixir crash course. First and foremost, Elixir is a functional language. So no mutability here. This has really been my first experience working with a functional language for some amount of time, and have really enjoyed how it helps change my thinking about programming, and how the different elements of a functional language really change the way you might build an application. It is dynamic, so it's not statically typed. There are annotations for types, but it is dynamic language. It is scalable and distributed. It's built on top of the Erlang VM and the decades of power and solidness of the Erlang VM. And one of the biggest features also is pattern matching. This is really my first experience using a language with pattern matching at its core. And that's been a very pleasant experience. For you Rubyists, it also has a Ruby-like syntax. So as a Rubyist myself, it was very friendly to get into from the beginning and get productive. We'll go over a few Elixir data structures. These are not all of them, but they are many of them that we'll be looking at today. There are tuples, collection of elements. These are used everywhere in Elixir, especially to return results, whether something was okay and then its result status. They're used a lot in message passing between processes. There are lists or arrays. They can be of multiple types, hold many things. There are maps with keys and values. Again, they can be multiple types, both the keys and the values within a map. And then there are structs, which act very much like maps, but they are of a defined structure, and you can even set default values for the elements and structs. So these are the basics of the data structures that we'll be looking at today in the code. So that's Elixir, that's the language side. Switching over to the Phoenix side of things. Phoenix is, first and foremost, a web framework. It was created originally by Chris McCord, and Jose Valim is now working on it as well, the creator of Elixir. It is Rails-like, but people are making it very clear in the Elixir community, it is not Rails ported to Elixir. Rails is very much based upon object orientation and mutability, whereas Phoenix is on an immutable functional language. And so it is Rails inspired, but it is definitely not a Rails port to Phoenix. And the other cool thing about Phoenix, especially with the power of Elixir and the power of Elixir's scalability, is that you can handle both typical request response cycles that you would in a normal web framework in Phoenix, as well as WebSockets. And so coming from a Ruby background, anytime you want to do WebSockets, you kind of throw your hands in the air and wonder what to do. But here in Phoenix, you can do them side by side and do them quite well side by side. So I really enjoyed that about Phoenix. But why Elixir and Phoenix? I've been doing Rails for many years, have helped scale a Rails app here at OrgSync. But really with Elixir and Phoenix, it gives you so much more power to scale a web app and help you to do things concurrently in a distributed environment in a functional language. It's really nice to have that request response and WebSocket backends living together all in one place. So that's been really nice. And the other cool thing about Elixir and Phoenix is that there's really a growing community around this framework. I've spent some time learning Clojure as well. And in the Clojure world, there's many different choices, whereas in the Elixir world, people are really centering around this Phoenix framework. And so you'll see a growing amount of support for it and a growing amount of people surrounding this Phoenix framework. But how scalable is it? What can you do? So over the last couple of weeks, there's been a lot of activity on Twitter about an example that using Elixir and Phoenix and how well it is scaled. And they've been able to use a single box, given it's a 40-core, 128 gig of memory box. They've been able to use a single box to maintain 2 million open client connections from WebSockets to this Phoenix application. And you can see from the memory and CPU usage doing quite well. And actually, they were limited by U-limit on the boxes. So that's pretty dang cool. But today, we're really going to dive in. And so we're going to take a look at an example, how you might structure an application. We won't cover all of the parts of Phoenix. In fact, I'll skip right over anything database because we won't be using a database today. But there is a library called Ecto, which is a really fantastic database interaction library used in Elixir and Phoenix. But today, we will be building a game because games are fun, and games are a great example of WebSockets and being able to do things live. So today, we will be building a game, but first, I want to give you a fair warning. What this is, it's an example of how you might structure an Elixir and Phoenix app with multi-process communication. What it is not, a good and efficient example in network game design. So I am not a network game designer. In fact, this is maybe my first attempt at a game. So there are a lot of things that could be more efficient here and to make it more performant, especially across the network and especially across the internet. But it makes for a good and fun example. So today we'll be building a game called Multitron. Multitron is a multiplayer Tron game. Allows multiple people to sign into a browser and play Tron. It looks kind of like this. You'll be able to give yourself a nickname. You'll be loaded onto this board where you'll be able to control your Tron line, wanting to not run into other people and not run into the edge of the boards, or you will fall off. And we'll do that live at the end. So what does the stack look like behind the scenes? You probably know it by now. We'll be running on the Erlang VM. We'll be using the Elixir language on the back end. We'll be using the Phoenix framework on top of the Elixir language. We'll be using primarily WebSockets to do all the communication. Everything will be WebSockets aside from the initial page load. And then on the client side, we'll be using React.js. And if you dig into the code base, which is open source, you'll be able to see the hot reloading aspects of it for development mode. And it's using local CSS to define your CSS individually for each component. But this is Elixir talk, so we'll talk mostly about the backend architecture. So the architecture of this thing. We'll be looking at primarily 3 different components on the server. Elixir is functional, and all of its functions are organized into modules. So we'll be looking at the game module, the game server module, and the game channel module. Then on the client side, of course, we have the browser. So let's take a look at the different responsibilities of each of these components. So first, the game module. The game module really defines the data structure for the game. In our case today, we'll be using a struct to keep track of the current game state. The game module will also define the various state transitions that you can make, and it will define how that data structure will be transformed from a previous state to the next state. And of course, it will contain any of the game logic that we might have for this Tron game, as far as are different players going to collide, are they falling off the board, what positions are they currently located in, and what is their current vector or their current direction they are traveling in. But it's important to note that the game module doesn't actually store the state. It merely defines how the state should be represented and how the state transitions should occur. The game server is actually what will maintain the state. If this were an object-oriented language, I would probably say at this point it keeps track of the instance of the game, but this is not. So it keeps track of the current state of the game, keeping track of that current game data struct. It will also handle messages to change that state and pass that off to the game in order to perform those state transitions. The game server will also schedule the game ticks. So in Tron, as the players move around, that tick will happen multiple times a second. So the game server will handle scheduling those ticks and performing them at a certain interval. So that's the game and game server. Game server will end up being a process that we run, a supervised process that we run in the Elixir ecosystem. The game channel itself is a Phoenix channel. A Phoenix channel is what handles WebSocket connections to and from the client. So with our game channel, we'll be able to send and receive updates to and from the client. It will pass those updates to the game server. The game server will handle transitioning the state of the game. And the game channel will also handle what happens when players leave and join. What happens if connections drop off, what happens when new players come in, and it will handle broadcasting all of the changes to all of the clients. In our case today, since this is a great example of poor network game design, the browser will be a very dumb client. The server will hold all of the state of the game, and the client will basically wait on the server to render that current state. So the browser will render the current game state, and it will send updates to the server given the user interaction. In our case, it will be mostly the keyboard. Any questions about the architecture here live? Cool. Okay, so we are actually going to dive straight into the code, look at some of this code of the game, and see how it all works. So first of all, what's going on here is we're taking a look at the Multitron application. This is an Elixir application running multiple supervised processes. This is one of the huge feature benefits of Elixir, allowing you to maintain and supervise these processes and handle anything that may happen if these processes crash. So there's a saying in the Elixir community, I think some people like it, I think some people don't. It is let it crash, or at least let it fail fast, because all of your processes in Elixir, if you built your application correctly, will be supervised and restart automatically. And so Elixir is really built and designed for you to be able to create fault-tolerant applications distributed across a cluster if you'd like. So in our Multitron application, what's going on here? We're defining our Multitron module, which represents our application. This is going to start up a supervisor. A supervisor is a process that supervises its child processes. And anytime any of those crash, it has a strategy to restart those. So in this case, we have our supervisor, which is the Multitron endpoint. This is the Phoenix endpoint, which controls the Phoenix application itself. And then we can see that alongside the Phoenix application, we have different processes that are also running. They really aren't even using any of the Phoenix technology. So we have a repo here. I could probably comment this out because this is the database side, which we won't be using today. But then you can also see I actually have two other modules running here. One is an ID server, and one is a game server. And game server was one of those components that we just covered. So let's go ahead and dive into the game. The game was that leftmost component that defined the structure of the game as well as its state transitions. So we can see here at the top, we're defining the structure of this game. This structure has a few different properties. It has a board size, which is a tuple of a width and a height. This is the default value, so if I create this structure without specifying this, it will have this default value. We also have a map of players, which will contain all of our players, the keys being the player IDs, and the values being another tuple of representing the player. And then we have positions, which will represent all the current positions of a player. Anytime you define a struct like this, the struct's name will take on the same name as the module in Elixir. So we'll go through a few different methods here to show you what's going on. Really, the public API of this, we have a few methods for adding a player, for removing a player, and for spawning a player. Adding a player is different than spawning a player because adding a player gets you into the game, whereas spawning will get you onto the board. So you could sign into the game, see what's going on, and then you'll see here in a little bit, you'll hit spacebar, and that will actually spawn you onto the board. So since we're not maintaining the state here, and since this is a functional language, we will always pass the current state in, and it will return a new game state. And you'll see this with pretty much every function in this module. So when I add a player, I'm going to take in that current game. That'll be the struct of this game. For this method, I'm going to pass in a player ID, and then I'm going to pass in a tuple. Now what you're seeing here is Elixir pattern matching. I can see here that I'm expecting a player. This tuple will be set to the value of player, or player will be set to the value of the tuple. And it's expecting 5 elements here. I've started all of these with underscores because I'm not going to reference them below, but I went ahead and documented that here in the method or the function signature so that I know what to expect. So I'm expecting a tuple of length of 5, passing in the name, the color of the player, the X and Y coordinates, and its direction. So these last 3 really represent a vector. I thought about making this a tuple of 3 and might change that up in a future version. All of that will be represented as player. So what will happen here if I pass in a tuple of length of 5 or tuple of length of 6? I will get a match error in Elixir. It will crash, and the supervisor will restart whatever called this with the incorrect signature. So what's going on here is fancy Elixir syntax, but basically it's taking the current game and replacing the value of the player's key with a new map of players. So we're creating that new map by taking the current map of players, and for the key of player ID, adding in that new player. This function will return the new game state, and that will be there and available. Similar for remove player, we'll go ahead and delete the player from the map and also delete any of their current positions. For spawn a player, we'll add them to the board. There's a lot going on there. I don't think it's that important. And then we also have a method to update the current player's direction. And so if they're traveling up, down, left, right. Hey, Matt, would you grab my water bottle off my desk, please? Now, if you've noticed as I've scrolled through here, some really large comments. This is because a really awesome feature of Elixir, they have doc tests built in. So anytime I have my doc signature here, thank you so much. Anytime I have my doc signature here, I'm going into documentation. You'll notice a few pound signs, hashtag signs here. That's because this documentation is Markdown by default. Elixir understands this documentation, and in fact, when you use IEX, which is the interactive Elixir console, you can type H and then the name of any method function, and it will give you the documentation. And if you structure your documentation with an examples area, you can structure it as if you were in the console. And the dot test will go through and actually run this code and test that it is equivalent to this value. So as you are writing your functions here, you can also write your documentation and also write your tests. This is not required. This is an opt-in thing. So you could certainly still have separate test files, especially for larger cases and more complicated cases. In fact, once you get down here and your tests look like this, this is probably a good time to move it off to a test file. But this is an example. Another very important part of the game is tick. Tick will handle whatever's happening at the tick of a game. So it will help move all the players and also calculate if they have collided. So that's an overview of game. It defines the structure and defines the state transitions. Yeah. Next up is GenServer. This is where we really get into a running Elixir process. And in fact, there is a thing in Elixir called GenServer, which is generic server, that helps you handle a common structure for how a process should run. So starting up the server, I have a few different things going on here. Start link is the default function that will be required or that will be called of any GenServer starting up by its supervisor. So that supervisor we looked at earlier that had the worker defined of GenServer, that's what that supervisor is calling right here to start this worker. And you'll notice I have two things. I have spawn link, which is spawning a function to be run concurrently. And I also have this thing called agent start link. And you'll notice that they both end in link here, and that's very important. So there's a function called spawn, and there's a function called spawn link. Spawn will spawn up a process running this function. It's basically a fire and forget, doesn't matter what happens. Spawn link will spawn up this function, run in a separate process, but if that function or that process fails, it will fail what called it. So if something if something inside of scheduled tick here fails, I definitely want it to crash my GenServer so that the supervisor can restart it. An agent is agent's a really simple way to help maintain state in this functional world. So we're going to start here with a default state of a game with all of its a game struct with all of its default values. And using the agent below, we'll be able to transition that value between different things. So GenServer is the server that's running the process that's running that my channel will then communicate with to do things. Man. So I have a couple of different methods here that the channel will end up using. First, it will get the game. So we'll get the current state from the agent. It can add a player. So we'll call the update method on the agent, passing in the current state, performing the transformation via the game module, returning the new state, and then that agent state will be updated. And this is how everything works in this module. Remove player, spawn player. We're really using agent update to take the current state, transition it with game, and store the new state. Update player direction and schedule tick. So up at the top, we did two things. We started up the agent, which started our maintainer of the state. And then also, concurrently, we spawned the schedule tick. So all of this stuff can be called at any time. And then schedule tick in the background will handle ticking the game at an interval. So we're going to sleep for a certain interval. This won't block because it's running in a separate, or it won't block the other processes because it's running in a separate process. And then we'll update the state by calling game tick on the current value of game. We will also then, after the tick of the game, we will call a serializer that I built to serialize this into a structure that's more JSON friendly. And then we'll use the Phoenix endpoint broadcast method to broadcast it via the game lobby channel and an update event. And this will take the serialized version of that game, automatically transform it to JSON, and then schedule the next tick to occur. So one last thing to look at, and then we'll play the game for a bit, and then maybe look at some of the client side. So game channel, we've looked at game, which is defining the structure of the game, how it transitions. Game server, which maintains the state. Game channel does all the socket communication. So we have a couple of different things going on here. Join is a function that Phoenix will call anytime a client joins the channel. I've called my channel game lobby here. That's the only channel I'm using today. It will send in a payload. If you wanted to do some authorization, you could. I'm not actually doing any authorization here. I also have another process running in the background. You might recognize ID server. We saw ID server earlier defined as another process or another worker process running inside the supervisor. ID server basically takes the PID. The PID is a process ID in Elixir, so any process has a PID currently attached to it. And each socket or current client connection has its own PID. So I'm going to take that PID and just generate a UUID that I can use over and over inside the game. And that will become the player ID. So we'll join and we'll just return that this is okay. They've joined just fine. Then the client will actually call an event to join the game, and that will get its player ID from the ID server. ID server is a running process. It will take the game server, which is a running process, add the player to it using the player ID and this tuple. And then a really nice thing about Phoenix, a layer that it builds on top of WebSockets, much like many Node and JavaScript WebSocket libraries, is the ability to do semi-request response within a WebSocket if needed. So I can actually reply here and tell the client what its ID is, because the client doesn't know yet until I return it from the server because I've generated their ID on the server. So this is handling an incoming message coming from the client of join. I also have only two other messages: direction, when the player changes direction, and then spawn, when the player wants to spawn onto the board and actually launch into the game. So spawn, pretty simple. It'll take the socket, pass it to the ID server to get its player ID. Then we have one of the many beauties of Elixir, the pipe operator, to actually pipe the value, the return value of this function, into the first argument of the next function called. Very much like the thread first operator in Clojure, or the thread first macro in Clojure. So the ID given back to us from the ID server will be passed to the game server to spawn that player on top of the board. And no reply here necessary because the game server will broadcast its new state out for us. And then once the player wants to change directions, the client will send a direction message. I am using atoms here to represent the various directions, up, down, left, right. Atoms are the equivalent of Ruby symbols. So I'm taking the string to an existing atom. I'm assuming from this method, this is not going to allow me to create a lot of atoms, like could be a memory leak in many Ruby programs. The same thing could happen here. So an existing atom into a direction. Again, same old, I'm grabbing the ID based upon this socket, passing that to the game server to update the current player's direction. So that's an overview of our 3 server-side components here. Again, we have game server, and game channel to handle these distinct responsibilities as a part of this game on the server. So we can actually take this game and play it for a few minutes, and then we can dive into some of the client side if you like. So word of warning, again, not the world's most efficient game channel. So we can try this over the internet, over Heroku, and then if that crashes and burns, we can try it locally here at OrgSync to see what goes on. So if you'd like to launch into the game, it is multitron.herokuapp.com. You'll be asked for a nickname, and then you should be able to start playing the game. So let's see what's going on here. And we have 3 live viewers too that hopefully could join us in the game as well. Somehow I knew Casey would use an emoji. Oh, that's Sailor. Oh. So you can use the space bar to start, and then you can use the arrow keys to change your direction. Once you run into something, the server, from YouTube, the server, hey, there's Steffi. The server will detect that collision and then remove all of your positions from the game state. That's pretty cool. Let me try here. So the score up at the top right are the number of movements you've been able to take without hitting something. And it will reorder based upon who's in first place. Tarantino's doing pretty good here. So what's going on is the server's using the Phoenix channel to, at an interval, broadcast the current state of the game. The current state of the game includes all of the players as well as all of their positions that they're currently in. And on each of those ticks, it will re-render using React here, the game. I started out with just simple DOM for the board with a whole bunch of divs for all of these boxes. I ended up moving to React Canvas to use Canvas from Flipboard. That actually hasn't been updated in a while, but it's still working if you use React 0.13. So the board here on the left-hand side is using React Canvas, and then everything else is DOM. So you can tell it's a little laggy, but it's not terrible, not that bad. I would love to use WebRTC. That would be cool. So we'll dive into a little bit of the client side here. Nothing too terribly exciting. So we have one main app component. The app component will put itself inside of a div, of course. It will style up the title of Multitron. I have a component here called Game Listener. This React component is really in charge of connecting to the channel, and anytime a new game state occurs, it will call its children via a function and pass in the current game state. So I'm separating out the concern of making sure I have the current state and then passing it into other components to render. So I have two views within this game. So down in my render current view function, I'm either going to render join if the user has not joined the game. That was the nickname box that came up at first. Or if you have joined the game, then I'll render the play component. So very simply down below, we have the join component and then the play component. The play component is another React component, and it calls itself, or it renders up both the board on the left-hand side, showing the current state of the board, as well as the leaderboard on the right-hand side to show the leaderboard of current scores of the game. And again, we're passing the game down into these components. So these components know nothing about sockets, know nothing about needing to communicate with the server at all. They're being injected that state from the props here. So if we take a look at leaderboard, it's rendering a simple table mapping over the players that came in through the game. So first I'm sorting the players by their current score. And so I'm calculating that score, or that, yes, I'm actually calculating the score here on the client side based upon how many positions that came back from the server. Sorting those by their score and then rendering them into a table here, one cell for the score and one cell for the name. And then back on the board side, this component's a little more complicated. Surface is provided by React Canvas that will actually render the canvas element on the page. And then I'm going to map over the players in the game. I'm creating a group, really just to group these layers up by player. And then I'm rendering a layer for every single position. And right now in the state, every single position is a point. So every little point that you've hit, it's not actually rendering lines, it's rendering a lot of different points at the same time. And then we have a style for that point to make it your color, to make it a certain width. And I ended up having to stretch out the width just a little bit because on a Retina screen, you could see little lines in between the points. And then I have a render instruction method. If you're not currently in the game, it will render your instruction to press spacebar to spawn you. This component is a little bit bloated because it not only handles the rendering of the board, but it will also handle a lot of the keyboard controls. So down below on my key down, I have a direction keys map up top to tell me if that key is up, down, left, or right. If it is one of those, then I will take the Phoenix channel, simply push a message that says direction and whatever direction I want to go. I don't need to reply back, no big deal, so I just let it go. And then also, if the key code is the spawn key, the space bar, then it will push a spawn message to the current channel. Again, no reply back because the server will handle that, pass it to the game server, render a new state. The new state will broadcast through the game channel all the way back down to my client. There is one more pretty interesting channel communication, and that's if you want to receive a reply. So whenever you first join the game, whenever you give yourself a nickname, this onJoin method will be called, passing in your name. I'm picking your color on the client side. And then through the channel, we'll push a message of join with the JSON object of that name and color. But different than the other messages we've been passing, we're expecting to also receive a reply back. So we're expecting to receive an OK. So if I go back to Elixir on join, I'm replying back with OK here, and then data. So I'm expecting to receive my player ID back, and I'm going to store that locally so that I can use that later, so that I know who I am on the board for rendering. Yes? What do you mean? Yes. Receive, I believe, will always be a tuple of two elements, one being kind of the status of the result, and one being actually the data for the result. So this could be a map given back, which will be transformed into a JSON object. It could be a string, it could be a numerical value, anything that's JSON friendly. Yes, so if there was the case for an error here, then over here I could have a different receive saying on error, giving some sort of error response and do something else. Definitely. Any other questions here? This is like a lot of different technologies going on here, but it's pretty cool. Yes?
Let's say that you, a generic question about throwing itself. Let's say that you have two separate actors, and let's say that one actor expects you to receive a message and then send another and then receive a response. Let's say it's like transactional and it has to know if it's received or not. Is there a way to register for a message with a timeout, something like that, rather than just receive a message?
Yes. So the question was, on the Elixir side of things, when you have multiple processes communicating with each other, can you handle kind of replies back, and can you surround those reply with timeouts? The answer is yes. I couldn't really run you through it right now, but that is possible. So within GenServer, which is what GenServer is using, start link is just one of the methods that could be defined on GenServer. There are many different other methods you could define to handle different types of communication. So whether you're expecting to receive a message that you will handle independently, or whether you expect to receive a message that you will also reply back to, there are different ways through, especially GenServer, to be able to handle that. I will repeat the questions, Eric.
Got one other question.
Yes.
It was in GenServer's file. You used a type operator to update the player state.
Yes.
With a new map. Is that recursive? Could you update the X coordinate within a particular, within one particular player or something like that? Could you reach into the structure and update the whole thing?
So the question was, is this syntax for updating values on a struct or on a map recursive so that I could reach into multiple values here, nested values really? This is not, but there is a way to do that. So I use this syntax here to be pretty plain and simple. It's also very struct friendly. There's another syntax that you can use on maps. I don't believe you can use it on structs, or at least I had a hard time with it. But it looks very much like this, and you'll recognize this as probably inspired by a closure macro. So if I had a map here, and I had the key of A, and then A was another map of keys of B and C. And I want to update that value of C to something else. C is a nested value inside two maps. There is a macro in Elixir, because there are also macros in Elixir, called updateIn. And so I could update that map and then give it a path of what I want to update. So in this case, I want to update the path of B, A. And then inside of A, I want to update the value of B to my new value. And so this would return me a new map with B having the value of new value. So that's really handy, but I don't believe it works on structs. I could be wrong. I would have liked to use that here because I am updating nested content.
One more question.
Sure.
What is the culture around macros? Are they avoided? Are they seen as the last resort?
That's a really great question. So the question was, what is the culture around macros? Are they avoided? Are they used as a last resort? Are they used everywhere? I've been in it for a couple months, but I went to ElixirConf in October. I've been reading lots of articles. Based upon my experience, I would say that the culture around macros is very healthy. They're only reached out to when necessary. It's not something that's used everywhere where you have to learn a new DSL every time you get into some new library to learn how to use it. It's very healthy. So an example is in Elixir for the router. Example in Phoenix, I should say. The router looks very much like a Rails router. So I have a scope here for my Phoenix router. So at the scope of root, I want to accept a GET request to the root of root. I'm going to pass that to the page controller and the index action. This GET is actually a macro that will transform this into a very simple function with pattern matching. So that's one of the huge benefits of Phoenix, is that its router is extremely, extremely fast because it's simple function calls with pattern matching that has been optimized in the Erlang VM for a long time. And so it's used sparingly, but used in places like this where it really makes sense and makes it easier than calling a function and having to structure this function in pattern matching. It would be a lot more verbose if you had to do that. Another really awesome thing about Elixir macros, unlike Ruby metaprogramming, Ruby metaprogramming mostly consists of dynamically defining methods, or worse, evaluating strings of code in order to run it. Elixir code is actually in AST. And so whenever you define a macro, you're taking the syntax tree of the code, destructuring it, manipulating it, and packaging it right back up. And so you're doing a very structured and organized manipulation of the code inside of the macro. Yeah. Any other questions? I guess I could check YouTube and see if we've had any come in. I think. Comments are disabled for this video. I didn't do that on purpose. Destructuring it, manipulating it, and I'm watching myself. Any other questions? Well, cool. You can check Multitron out on GitHub. I'm realizing now I didn't put in a slide for that. So it's github.com/Multitron. It's all open source here. It's this full example. So how you might structure the Elixir code with the Phoenix application, the React code running with Webpack to compile it, along with local CSS and hot reloading on the client. So there's a ton of stuff packed in here, as well as what it would require to deploy this to a Heroku instance. The deployment to Heroku is pretty simple. There are 2 different build packs that you'll want to run. And then if you're like me and you rip out Brunch and put in Webpack, then there's a simple compile file that you can define to specify how to compile your assets. So very simply, I want to run Webpack in production mode and then make sure to digest those assets so Phoenix knows where to find them. So other than that, a few closing notes here. If you liked this Lunch and Learn, we do this quite a bit at OrgSync every couple of weeks. The dev team here shares whatever we're learning, whatever we're working on. So we have a Twitter account called OrgSync Devs that you can follow, and we'll tweet out about our Lunch and Learns. You can watch them live on YouTube, and then they'll be available publicly afterwards. And also, while we aren't doing any Elixir in production at OrgSync, we're doing lots of other cool things, and we are certainly hiring and trying to find people. So if you have any interests in Ruby or Clojure or Node.js or React or iOS or Android, then we are hiring for all of those areas. So cool. Thank you for attending, and I hope you enjoyed.